Hey folks, in this video we're going to talk about LC circuits, inductor capacitor circuits. And I've drawn a picture of a mass oscillating horizontally with a spring. If you get a moment, or if you take a moment to sketch that out, we're going to actually review that process because it turns out that LC circuits are the same process. All right, so hopefully you've paused the video at some point and copied that picture down. All right, so quick recall here. We know that for that system, force, mass in a spring, we know that the spring force is equal to negative kx, right? The negative is all about direction. If you pull the mass to the right, the spring is going to pull left. That's why the negative is there. We also know that net force on the mass is equal to ma. Assuming there's no friction or anything, this would be the only horizontal force. So if you put those together and solve for a, you get negative k over m times x, okay? A is the second derivative of x. This is a second order differential equation. So you can rewrite this as the second derivative of x equals negative k over m times x, right? And we also talked about for simple harmonic motion, whatever's in front of the x is omega squared. So we know omega squared is equal to k over m. And we also know that period of the oscillation will be 2 pi over omega. So for instance, this would be 2 pi root m over k, right, for this mass in the spring. So that's all review from simple harmonic motion. Also a quick review of graphing. Okay, so if we were graphing this motion, okay, and we had, let's say that's 0, a quarter period, a half period, 3/4 period, full period. So I'll label that quarter t, half t, 3/4 t, and period. All right. If we were to graph, let's say position. So let's say, for instance, we started with this cart all the way over here. So x is a, the max amplitude, and it's positive. Okay. So x would start up here, and then you would have a nice, this would be, I guess, a cosine curve, and it would go like that. Okay, so that would be x as a function of time. Velocity, well, the velocity would start off at the very end of this motion, the velocity is 0, and then it's going to be negative shortly thereafter. So our velocity would start here, and it would be like this. And so we have a phase shift, basically, right? Okay. And then you could also graph acceleration. Our acceleration is a max negative here, and it's going to tend towards 0 when it gets to equilibrium. So let me label the velocity, sorry. So that's the green is the velocity, and then acceleration would start as a max negative. That would be a, and it would go like this. So that would be your acceleration. That would be a, okay? And that's the exact opposite of x. Notice that, hey, a has the opposite sign of x, right? So that's not a surprise, okay? So that's a review of simple harmonic motion in 3 minutes, all right? Now, why are we doing this? Well, it turns out that an LC circuit behaves exactly like a mass bobbin left and right on the spring. So let's say you have the following. Let's say you have a fully charged capacitor. So it's sitting here all charged up, ready to go. There's your capacitor. And you have an inductor over here. Okay, so we have an L, and we have a switch right there. And we want to know the charge on the capacitor as a function of time. Okay. Well, we're going to do this basically the same thing we just did up here. Okay. So we're going to start with Kirchhoff's loop rule. Okay. And I'll start here and go clockwise or counterclockwise. Okay, so we're going with the capacitor. So that voltage would be Q over C, and then we're going through the inductor, so that would be plus L di dt, and that all has to equal 0. In other words, Q over C is negative L di dt. In other words, one voltage has to be positive and one voltage has to be negative if you go around the loop, okay? Now, di dt. So remembering that I is dq dt, then di dt would be the second derivative of charge. So you get q over c equals negative L d squared q over dt squared. Okay, so we have our second order differential equation again. I have to get, just like up here, I got acceleration by itself. Down here, I'm going to get d squared q dt by itself. So d squared q dt squared equals negative 1 over LC times Q. All right. So whatever's in front of the Q is omega squared. Okay. So omega squared is 1 over LC. So omega is root 1 over LC. So now we can write, just like with simple harmonic motion, okay, if it's a second order differential equation, you can write things like the position would be x equals a cosine of omega t plus some starting angle. Now, in this case, phi would be 0 because cosine of 0 is 1, and that's where we're at. Velocity would be dx dt, right? The derivative of that, which would be negative a omega sine of omega t plus phi, okay? And then acceleration would be the derivative of velocity, which would be negative a omega squared cosine of omega t plus phi, right? And by the way, that's why whatever's in front of your x is, or whatever's in front of your x up here is omega squared. This is y, okay? All right, so we're going to do the same thing down here. So Q is going to have this function, okay? Now, what's the amplitude? Okay, well, that's just Q max. So Q is going to be some maximum starting value, whatever that was, whatever the fully charged capacitor was, all right, times cosine of omega t plus phi. Now, again, that phi is a starting condition that depends on where you're at in this process. In other words, when you close this switch, where is the charge at? Now, in this case, the charge is all on the capacitor, so we would say phi is 0 here, okay? Well, then we can also write current, okay? Current is a derivative of this, dq dt, which is negative q max omega sine of omega t plus phi. Now, there's not really a reason to do the second derivative of this. You could, but there's no reason to do it. So what's going on here? Okay, well, when you first close this switch conceptually, okay, so let's talk conceptually for a second. When you first close that switch, what does the inductor try to do? It tries to keep current from flowing. So at first, the current will be 0. But as time goes on, and again, I'm going to pretend it's positive moving. We know better, but let's pretend. As time goes on, more and more charge will begin to flow through the inductor as the capacitor discharges. Well, at the moment that the last charge is leaving the capacitor and the capacitor is fully uncharged, your current will now be a maximum, okay? So then what's going to happen? Well, the inductor is going to try to keep that current flowing. So even though this plate up here will be empty of charge, the inductor will keep current flowing, which means it'll suck more positives off that plate, which means the plate will start to become negative and you'll start depositing excess positives on the bottom plate. As that happens, the current will slow down until the capacitor has the reverse charge that it started with. That's exactly like what happens up here. If you start with this mass over here, you let it go, the mass increases its velocity until it gets to here. At that point, the net force on the mass is 0. That means you've reached a max velocity, so the mass will keep going, okay? So that's exactly what happens to current over here. When the capacitor is fully discharged, that's when your current's a maximum, so the current will keep going, and the mass will reverse its position. The charge will reverse its polarity on the capacitor, okay? Now, we can graph this too. It's very similar. So if I were to graph these two things, like so, all right, so charge started off at a maximum, that was Q max, and it's going to follow every quarter period. It's going to going to go like that, right? It's going to be a cosine curve. Our velocity, or our current, sorry, our current starts at 0. It starts off negative, so it's going to start off going this way, because we, like so. Okay, there we go. So it's going to trail the charge by a quarter period. It's going to be shifted a little bit. Okay, so, and again, it's because when the charge is 0, the current's a max negative, and then when the charge is a max negative, okay, that means we're at this position, or at this position now with the green, then the current is 0, and then it reverses itself. Okay. Now, one last thing I'll mention, the energy. Energy of a capacitor is Q squared over 2C. That's one equation for it. The energy stored in the magnetic field of an inductor is Li squared over 2. Okay. These are going to be equal at the maximum value. The total energy in the capacitor when we start will be equal to the total energy in the inductor when the current's the maximum. Okay. The total energy at any point is going to be this as a function of time plus this as a function of time. Again, here's our charge and current as functions of time. Okay, so let's write this out. So for the capacitor, it would be Q max squared over 2C cosine squared of omega t plus phi, plus for the inductor, it would be L I max, which is Q max omega. So that would be, and that's going to be squared. So Q max omega, okay, like so, squared over 2 sine squared of omega t plus phi. Okay. Now remembering that omega is 1 over a root 1 over LC. If we plug that in here, look what happens. You get a Q max squared over 2C cosine squared of stuff, okay, plus an L Q max squared omega squared, which is 1 over LC, all divided by 2, and sine squared of stuff, okay? So let's write this out a little further. You get Q max squared over 2C cosine squared of stuff plus, all right, what happens here? The L's drop out, and you get Q max squared over 2C, sine squared of stuff. And you can pull the Q max squared over 2C out, and you end up with cosine squared plus sine squared. But what's cosine squared plus sine squared? Well, it's 1. What that's telling you is the total energy in the system never changes. It just sloshes back and forth between potential energy stored in the capacitor and energy stored in the magnetic field of the inductor. Just like up here, spring potential energy turns into kinetic energy, and that sloshes back and forth as the mass bobs back and forth on the spring. Okay. One last thing I'll do just for fun is we'll graph potential energy stored in the capacitor as a function of time and potential energy stored in the inductor as a function of time. We'll do every quarter cycle. Okay, so this would be period right there. Okay. Now, these are squared functions, so they're always positive, right? We're doing, like for the capacitor, we're doing cosine squared. So that starts off at a maximum, and then it's 0, and then it's a maximum, and then it's 0, and then it's a maximum, because it's squared, it's always positive. And so you'd have something like this. Okay. For the inductor, we've got a sine squared term. So that starts off at 0 and then does something like this. Okay. And no matter what time you pick, this plus this will always equal the same thing. Okay, the sum of the energy of that's stored in the capacitor and stored in the inductor always has to stay constant. Okay. All right. So again, a mass bobbing left and right on a spring, elastic potential energy and kinetic energy, it's the same as charge bobbing back and forth in an LC circuit. energy stored in the capacitor and energy stored in the inductor oscillate back and forth as the charge oscillates back and forth, just like a mass in a spring. The cool part is, the last thing I'll leave you with, a lot of systems exhibit this behavior. So these are just two of the systems that exhibit this behavior. Once you understand the behavior and the math behind the behavior, studying that behavior in all kinds of systems becomes a lot easier. All right, I hope you found that video helpful, and thank you very much.